Thank you. So this is quite a challenge to try to bring you down from the heights of science to the lowlands of commercial lasers and business. I'll try it anyways. When Charles Darwin visited the Galapagos Islands on his 5-year trip on the Beagle between 1831 and 1836, he made a curious discovery. He noticed that the beaks of birds that he mistakenly identified as finches, they're now called the Darwin finches, vastly differed from island to island. In total, he identified about 14 to 15 different finches with different beaks. And this was curious insofar as that they must have had a common ancestor. But the beaks had quite dramatically adapted to the food sources available on the islands that the birds lived on. The question I want to discuss today is whether in lasers in manufacturing we have a similar situation. Is there a common laser design or laser technology platform that is adaptable enough to address many different applications, just like the beak of the Darwin finch had adapted to different food sources? Or do unique applications, do different applications, you need unique laser concepts? The answer to this question is quite important for laser manufacturers and for the laser industry in commercial lasers as a whole. Today, the market indicates that unique laser designs are necessary for different applications. This leads to a business model where we have relatively high R&D costs because we need to, in parallel, support different laser platforms. And thereby, we also have harder to achieve economies of scale. Therefore, the laser remains a relatively expensive tool, and because of this, its use remains limited. However, obviously, if one design were adaptable enough to address most applications, the opposite would be the case. R&D costs would be lower, and economies of scale would be higher, and therefore the cost reduction of the laser as a tool would be a logical consequence. So the question whether the variability of the laser platform is sufficient for many food-gathering purposes, to state with the example of the beak, is very important. Before I want to discuss this question, let me briefly introduce the company that I work for, the company TRUMPF. TRUMPF is the world market leader in machine tools for fabricating sheet metal, and it's also the market leader worldwide for industrial lasers. We were founded in 1923. Our headquarters are in Stuttgart, Germany. We have about 9,000 employees worldwide. 1,000 of them work in the United States. We have subsidiaries in all major economies. We're organized in 3 divisions: machine tools, as you can see, for sheet metal fabrication, industrial lasers and electronics, and medical systems. Our business model is somewhat unique in such as that we are probably the machine tool company that knows most about lasers, or vice versa, the laser company that knows most about machine tools. In lasers, we do all major technologies. This is an important fact because, of course, it shows the subjectivity of my analysis. We do CO2 lasers, fast flow, and diffusion-cooled solid-state lasers, diode-pumped solid-state lasers, fiber, disc, and rod-based. We make marking systems, ultra-fast lasers for manufacturing purposes, diode lasers, and laser diodes. Our revenues in the past fiscal year were at about 2.75 billion euros. Revenues in the business field of lasers was about 915. We spend 8 to 10% on R&D, about twice that amount in the laser field. During the last economic recession, we were hit very hard, but we recovered. And over the last 50 years, we've had a CAGR of approximately 15% annually. But let me get back to my question. Is there a single platform that is adequate and adaptable enough to do many different applications. In order to be able to discuss this, I think it is necessary to look at the industrial laser market as it is today, and then also to look at some of the applications that are important in this market. The industrial laser market obviously is part of the general laser market, but with about 35% of the revenues of the entire laser market, it is the most important laser market. Looking at industrial laser revenues by technology, you can see that the revenues between the laser sources are split up and between sources that are fundamentally different. It shows that today there is no single laser source that is able to cover most applications, or at least that the market hasn't developed in that way yet. Within the industrial laser market, laser cutting by far is the single most important application. Cutting is followed by welding with about 15% and marking with about 12%. The applications semi and micro and other really are a large number of applications that vastly differ from each other. In these clusters, semi, micro, and other, we find applications like thin film solar cell scribing, wafer cutting, matrix lead frame cutting, microlithography, cutting of hardened glass, stent cutting, to name just a few. Each of these applications demands today its own laser source with vastly different specifications and application development. I've tried to cluster a few of those applications to give some examples of the parts that are being made by them to generate a better understanding of the breadth of the applications that I'm talking about. The market for industrial lasers has shown rapid growth over the past years. I cannot think of many capital goods markets that have produced a CAGR of about 20% over the last 20 years. So how will the market develop in the future? Well, obviously, I'm no analyst, but I have an opinion about this. I think that this growth will continue. However, the major growth driver of the past, which was laser cutting, probably will not be in that role in the future. I think that micro applications, or what I described as other applications, will get into the role of being the growth driver, simply because there are new laser sources available today that were not available in the past and that are driving new applications. From the aforementioned breadth of applications addressed by industrial laser derives a set of laser characteristics that are necessary. I have clustered these characteristics and named them capability, reliability, and cost. Capability such as laser power, beam quality, wavelength, pulse length, pulse shape, just to name a few, have to be delivered reliably to ensure productivity and robustness both of the systems and of the process itself. Thirdly, costs such as investment, running cost, and the ability to simply integrate the laser source into a laser system play an important role. As an example for an attribute that I called capability of the laser, I'm using a well-established chart that graphs beam parameter product over power and overlays this with specific applications. Simply put, different applications need different power levels and different beam parameter products. Picking the largest application that I mentioned before, laser cutting, out of this chart, the capability of the laser necessary for this application turns out to be a beam source at about 1 to 8 kilowatts of output power and a beam quality of roughly between 4 and 20 millimeter milliradians. The application demands no pulsing. It's a CW application. But what about other attributes or specifications such as wavelength? Currently, there's a heated debate going on in the market whether, whether 1 micron or 10 micron wavelength is more suitable for cutting metals. In other words, whether the CO2 laser or the diode pumped laser can do a better job. Looking at the impact of the wavelength more closely, it becomes obvious that the laser attribute, this laser attribute, does have a major impact on the application itself. We're seeing that on one hand, going to the shorter wavelength, the productivity of the process increases in light gauge material. However, the flexibility and robustness of the process with the shorter wavelength is worse because it is you are no longer to cut thick material in a burr-free way. Comparing the two wavelengths in stainless steel, this can easily be seen. Cost is another characteristic we need to consider in this example. The running cost of the diode pumped laser is theoretically lower because of its higher efficiency. However, the invest for an equivalent CO2 laser is substantially lower, with CO2 lasers today reaching $30 per watt laser power, which is much less than a comparable diode pumped laser. Obviously, with this example, the answer that one single technology can do the job is no. To the question is no. Using the same approach, looking at another application, the question of pulse length can be discussed. An important application in the automotive industry is the drilling of very fine holes that have to be extremely accurate in metals for the manufacture of fuel injection systems. There have been attempts to use nanosecond lasers to do this. However, the results were not satisfactory. For years, the holy grail of this application seemed to be femtosecond lasers. However, they lacked power and were too expensive to be deployed in the automotive industry. The solution finally came with the introduction of very high average power diode pumped picosecond lasers based on the thin disk technology. A sweet spot was found for the application where good edge quality, high productivity, and relatively low cost for the laser beam source was available. So in this case, yet another basic technology, the thin disk laser, was necessary to achieve the goal. Getting back to the question of required laser characteristics, I would like to briefly discuss the issue of reliability. Reliability, of course, is a function of the robustness of the laser concept, which again depends on the complexity of the laser system and the technology readiness level of the ingredients of the subsystems that make up the laser system. Regardless of the above, the serviceability of the system is very important. No technical system is infinitely reliable, which makes the serviceability designed into the laser vital. Reliability and robustness, again, are inversely linked to cost. The reciprocity of reliability and cost is easy to understand with an example. A laser, for instance, going into space on a satellite to analyze the atmosphere will have higher reliability cost built into it than a laser going into a line where keypads are marked that sits next to hundreds of similar lasers. And reliability and robustness are relative because they depend on the environment that the laser operates in. I have some examples of some environments on the wall. A laser, for instance, that is used for wafer scribing in a clean room of a semiconductor fab will have a different reliability than one that is used for butt welding of coils in a steel rolling plant. Yet again, I think it becomes obvious that when looking at the characteristics of reliability, that it is unlikely that a single technology platform is suited to serve all applications. One of the most important factors I still have to discuss is the question of cost. In the issue of cost per watt of laser power delivered, we've had quite a dramatic development over the past years. This development was driven, of course, by the development of laser diodes becoming vastly more powerful, and as a result, diode-pumped solid-state lasers, be it fiber or disc, have seen dramatic cost reduction. We have experienced something that I would say is comparable to Moore's law in the last 10 years regarding the cost for available laser power out of diode pumped lasers. I don't expect this development to continue at the same pace, simply because only about 30% of the cost of a laser, diode pumped laser, are made up from the cost of the diodes themselves. The cost erosion, therefore, must slow down. Nevertheless, this development has enabled the diode pumped laser to compete in applications such as metal cutting, where it could not compete before. I still don't believe that this cost development will lead to the dominance of one technology of the diode pumped laser for the reasons I mentioned above. So, if it is not possible to address many applications as a laser manufacturer with one type of laser, would it then make sense to instead cherry-pick application and focus on a few applications only to limit the span of technologies one has to manage? It could be best for a laser manufacturer to focus on these individual applications. When defining the strategy for my company in this question, we found that 3 reasons speak against this strategy of only addressing individual applications. First, I think addressing many applications with different platforms leads to cross-fertilization and new business opportunities. Developing industrial laser applications broadly and simultaneously in areas such as cutting, welding, marking, engraving, etc., leads to a much broader understanding of laser applications in general in materials processing, and thereby it leads to a more fundamental understanding of the individual application in question. Secondly, the question of economics of scale plays a role. Focusing only on an individual application will lead to problems of economies of scale because you cannot then do it globally. Most laser applications are relatively small niches that do not support a worldwide operation. Thirdly, we have observed that in many cases, customers do not only have one application, but many applications, and it is better, therefore, for the laser supplier to be able to offer many solutions to the same customer. It will strengthen the customer-vendor relationship. Clearly, for my company, the answer to this question, does it make sense to focus, is no. So if it is our desire to offer lasers that address many applications, and we want to at the same time limit our R&D spending, how do we do it? Well, when at the beginning of a laser project, an R&D project for a new laser for a new application, we try to determine which technology we base this on. To achieve this, we go through a list of criteria. Obviously, the first question is, can the platform that we choose achieve the specs that we need? But the second question might be more important. Is the scalability of the platform in respect to the most important single specification, for instance, output power, is that given? Third is then the question of the complexity of the system. Fourth, the question of robustness and serviceability, and so on. As I said, in my mind, the question of scalability regarding one or two of the most important specifications is imperative, because it will lead to the effect that a few laser technology platforms will be able to serve many applications. If applied well, this concept leads to an optimal relationship between R&D spending and the breadth of applications that we can serve. With a few laser platforms that are scalable, many applications can be addressed. 2 examples of scalable laser technologies, and this will surprise you or maybe not, are in my mind the CO2 laser and the disc laser. In the case of the CO2 laser, the scaling capabilities that I want to mention are power and the ability to produce very short and very powerful pulses. Originally, the CO2 laser, the fast flow CO2 laser, was developed to be a powerful and reliable and low-cost laser platform with ideal properties for laser cutting of metals. In the past years, our company, TRUMPF, has expanded this laser technology as a technology platform to be suitable as a pump for EUV light sources. The technology for the EUV light sources was developed together with Cymer in San Diego and ASML in Holland. And we are now beginning to deploy these types of EUV sources based on the CO2 laser at all major semiconductor manufacturers worldwide. So the scalability of the CO2 laser in this case allowed us to enter to entirely new fields. Next example, disc laser, which was developed by us as we felt, an ideal laser for industrial applications where high power and good beam quality at a low cost and high reliability was needed. The result, of course, is the most successful high-power welding laser worldwide. The interesting thing, of course, again, is the question of the scalability of this platform. The scalability is now taking place, or the scaling is now taking place in several dimensions. One, beam quality. We are, at this point, deploying high beam quality disc lasers as cutting lasers worldwide for metal cutting applications and have achieved a market share worldwide of approximately 30% in this technology. At the same time, the scaling of this technology platform is taking place in an entirely different direction, in the direction of picosecond lasers. Based on the thin disk platform, we are realizing picosecond lasers at high power using the principle of regenerative amplification. And thirdly, we're scaling this technology platform for the use as nanosecond lasers of very high power of several kilowatts by using the principle of cavity dumping. Again, you can see that one technology platform can be expanded and many applications can be served. You recall the chart that I showed in the beginning about the Darwin finches and their beaks. The same, in my mind, does not apply for industrial lasers. The breadth of applications in industrial lasers and the variation of the boundary conditions is just too vast to be covered merely by one laser technology platform. But the good news is that a successful strategy exists. The strategy is to identify scalable laser technology platforms and to focus on them in an approach where as few as possible of them are used to cover as many applications as possible. Amongst these, as I mentioned, in my mind, is the thin disk technology, where we have a platform that allows very high optical power, output power, at high reliability, at low requirements regarding the brightness of the pumps, and thereby low cost of the system. Second platform, of course, is the fiber laser with its unique attribute of monolithic design on one hand and its ability to simply produce fundamental mode light and its power scalability. I think it's the ideal platform for applications where either fundamental mode light is necessary or where compactness at high power is needed. The third, in my mind, is the CO2 laser with its unique attribute producing light at 10 microns wavelength, which is very good for cutting metals, its competitive dollar to watt ratio, and its rock-solid robustness. I think it will remain the most important laser for metal cutting. And fourth, of course, is the diode laser technology with its unrivaled efficiency and compactness. It will become more important than it is today if and when it will be able to produce high power at high brightness, also because of its ability to produce different wavelengths. But there are other good reasons, I think, to follow the strategy of the multi-platform concept. First and foremost is the fact that the industrial laser company that offers the choice of several platforms can offer the beam source that best fits the application. This is not the case when following a single platform strategy. Secondly, I have witnessed many times that in the multi-platform approach, the unexpected application happens. The EUV light source is a good example for this. This by no means was on our radar screen 10 years ago, and yet today it's one of our most important applications. And lastly, in a company where different laser technology platforms are pursued, there is internal competition. And this is something that keeps you sharp and makes you better. So in conclusion, I'm happy about the result of my analysis because I think this way the world of industrial lasers will be a lot more interesting than if only one platform did it all. Thank you very much.